In this lecture, I'm going to focus on the chemistry of carbon, which is by far the most interesting, the most versatile of all the chemical elements. This versatility follows from the great principle of carbon chemistry, that is, that carbon forms strong, covalent bonds with itself, as well as many other elements. The main objective of this lecture is to explore the absolutely astonishing diversity of chemical compounds that result when you begin with element 6, the element carbon. I'll begin by just focusing on the simplest compounds, called hydrocarbons, which combine carbon and hydrogen only. Then we're going to add other key elements, oxygen, nitrogen, and so forth, and the complexity will get greater and greater. I'm also going to be introducing two new kinds of interatomic forces called van der Waals interactions and hydrogen bonding. And these help hold many of the carbon-based compounds together. Before we get started, in all fairness, I have to give you a warning. Carbon chemistry, which is also known as the field of organic chemistry, has a really bad reputation. Organic chemistry strikes fear in the hearts of science undergraduates everywhere. It causes many otherwise confident scientists to shake their heads and cringe. You see, carbon chemistry is exceedingly rich. There are literally millions of different carbon compounds, and so there are literally millions of different names. A typical organic chemistry course may introduce hundreds, even more than 1,000 new names to be memorized. Well, you can't get away from it. You see, scientists have to communicate with each other, and the only way to do it is with names and with formulas. Well, that's the downside of carbon chemistry. That's the downside of organic chemistry. But the upside is that the richness of organic chemistry elevates it from a science to virtually an art. The most skilled organic chemists are like great sculptors. They imagine incredible three-dimensional molecules, and then they build up those molecules atom by atom by atom. Only in this case, these aren't just sculptures for aesthetic reasons. These sculptures feed people. They provide clothing and shelter. Indeed, they relieve pain. They cure disease. Like any art form, you can't appreciate carbon chemistry until you know the basic rules, the grammar of the art form, if you will. And that's what this lecture is all about. My outline is in 3 parts. First, we're going to look in detail at carbon, element 6, and its unique bonding strategy. And that's to share up to 4 electrons with up to 4 adjacent atoms, including other carbon atoms. Understanding why carbon bonds the way it does is the absolute key to understanding organic chemistry. Then we're going to use that strategy to assemble various carbon-based compounds. I apologize in advance for using lots of new chemical terms. You may find that it helps to follow along in your booklet where there's a guide to organic molecules and their chemical formulae. Finally, I'm going to introduce 2 kinds of intermolecular forces, van der Waals attraction and hydrogen bonding. These forces help to hold the organic molecules together. So let's begin by thinking about the strategy that carbon adopts in its quest for chemical stability. Recall from the last lecture that chemical bonds reflect the tendency of atoms to try to find a filled shell of electrons, that is, either 2 electrons or 8 more, which gives you 10 electrons, or 8 more than that, which gives you 18 electrons, and so forth. Those are the filled shells, which are particularly stable. So we have ionic bonding, in which one atom gives up an electron and becomes a positive ion. Another atom takes up that electron, becomes a negative ion, and the ions bond together through electrostatic forces. And we had metallic bonding, where all the atoms in the collection give up some electrons, form a negative sea of electrons, and then their positive charges interspersed, and that holds the metal together. And finally, covalent bonding, in which just a few atoms together share their electrons so that every atom sees that magic number. Each of these strategies, that is to accept electrons, to share electrons, to give away electrons, can result in lower energy. Now, while there are only 3 different kinds of major chemical bonds and only a few dozen different common chemical elements, there's an endless variety of chemical elements and compounds that can be formed. That's because the 100 or so different chemical elements of the periodic table can combine in so many different ways. And in this regard, carbon is unparalleled. It forms covalent bonds with up to 4 different neighbors, including bonds with other carbon atoms. And this ability means that you can devise larger and larger and more complex structures just by adding more carbon atoms. In fact, more than 90% of all the known compounds in chemistry are carbon-based compound. And by far, organic chemistry is the largest subject in chemistry today. There's also industrial reasons for this. The total production of organic chemistry is just vast. It includes all the plastics, all the paints, the glues, the drugs, the cosmetics that we use, and also the fuels, gasoline, kerosene, natural gas, heating oil. Indeed, the total amount of organic chemistries produced in North America alone is more than $1 trillion a year. That's big business. Well, the geometry of carbon is illustrated on the periodic table. Carbon is element 6. And the 6th element wants 4 more electrons. The key to organic chemistry, then, is to figure out a way for carbon to gain those 6 electrons. Think of this as a kind of game. A game in which the rule is that carbon is looking for 4 more electrons, and in the process, it has to help all the surrounding atoms satisfy their magic numbers of electrons. In concept, then, the rules of this game aren't very difficult. So let's start by just considering the varied compounds of carbon and element 1, hydrogen. These are called hydrocarbons, and hydrocarbons are extremely important in our lives. Natural gas, methane, is a hydrocarbon. The butane of butane lighters is a hydrocarbon. Gasoline, hydrocarbon. Many other of our fuels, even candle wax, is a hydrocarbon. So we begin with a single carbon atom. Now, if you're listening to these lectures on audio tape, I want you to imagine a single letter C. And that C, that carbon atom, needs 4 more electrons, which will be represented by 4 little lines coming off the letter C. So along come 4 hydrogen atoms. And each of those atoms needs 1 extra electron to reach their stable number of 2. And here's what happens. It's an easy solution. The 4 hydrogen atoms surrounding carbon each share an electron, so they see 2, a pair of electrons. And the carbon, which initially has 6 electrons, sees the additional 4 electrons that are brought in by hydrogens. So the carbon sees its full complement of 10 as well. What you have then is CH4. That's the simplest hydrocarbon called natural gas or methane. It's a rich energy source. A key reason for the variety of carbon chemistry now lies in the fact that carbon can easily bond to itself. That's an amazing ability. You can have 2 carbon atoms that share a pair of electrons with each other. That's called a carbon-carbon single bond. And you can imagine this as 2 letters C with a single line drawn between them. That single line represents a pair of electrons, 2 electrons that are shared between the 2 atoms. And then if you want to, you can add hydrogens all around the outside, and you come up with C2H6. That's the chemical called ethane, also a very efficient fuel. And you can always play the game this way. You can always take away a hydrogen and replace it with a group of carbons and 3 hydrogens, a CH3 or a methyl group that just sticks on the end. So methane, which is CH4, becomes ethane, C2H6. And then ethane becomes propane, which is C3H8. That's also a very efficient fuel. By the way, if you keep on substituting carbon for hydrogen in this process, that is, every time there's a hydrogen, take it away and put a carbon on instead, you eventually wind up with a structure of diamond. You see, diamond, which is pure carbon, is surrounded by 4 other carbon atoms. Every carbon atom is surrounded by those 4. So you can see this beautiful framework structure of diamond in which every carbon atom is the center of 4 more. And in this way, every carbon atom is fully satisfied with 10 electrons. That's an incredibly strong three-dimensional framework, the strongest material known. Okay, back to hydrocarbons. You can go from methane with 1 carbon to ethane with 2 carbons to propane with 3, butane with 4, and so forth, just by taking away hydrogen and replacing it with CH3 groups. Normal alkanes include a large series of covalent bonded material in which there's just a long straight chain of carbon. You can have 4, you can have 10, you can have 100 carbons in a normal alkane. These are backbones, long straight chains of carbon surrounded by hydrogen atoms. And you use these straight hydrocarbons all the time. Propane is a common fuel. Butane, the kind of fuel that you use in butane lighters. You also have straight chains of carbon in typical candle wax, typically molecules of about 20 carbons in length. Now let's remember a key point here. All of these compounds have carbon in which the 6 electrons of carbon are searching for 4 more to reach the magic number of 10. That's the game we're playing here. And you can play the game in other ways. You can have branches. So for example, the simplest of the branched hydrocarbons is isobutane. It's 4 carbon molecules in a T-shaped, 3 across and 1 down. Now, isobutane differs from normal butane, which has 4 carbons in a row, but the chemical formulas are exactly the same. In each case, C4H10. Normal butane and isobutane are called isomers of each other. Same composition, but different structures. And as the number of carbon atoms increases one by one, the number of isomers increases exponentially. Pentane has 3 isomers. You can have 5 atoms in a row, 5 carbons in a row. You can have 4 carbons with 1 branch, or you can have a cross of carbons with those 5 carbons. Now, hexane has 6 isomers, and you should try drawing those yourself. When you start getting alkanes with 20 or more carbons, the number of isomers runs into the thousands, becomes an incredible problem. One of the most important of these hydrocarbons is octane. That's with 8 carbons, and it has 18 isomers. One of the most important of these is isooctane. That has a backbone of 5 carbons, and the middle 3 carbons have single carbons coming off as little tiny branches. It turns out that isooctane is particularly effective at stopping knocking in your car's engine. And this is in contrast to normal heptane. Heptane has 7 carbons in a single backbone, which is particularly bad in this regard. So when you buy gasoline, you have an octane rating. The scale goes from 0 for pure heptane to 100 for pure isooctane. A new wrinkle is provided by cyclic hydrocarbons, in which carbon atoms actually form a ring. And you think about it, in this case, each carbon sees 2 neighboring carbons, and it has 2 neighboring hydrogens. So every atom is happy. One common ring molecule is cyclohexane, C6H12, with that 6 carbon ring. Now, it gets even more complicated because cyclic hydrocarbons can also have branches, they can have chains, you can have a chain linking 2 rings, you can have nested rings, any imaginable combination of carbon and hydrogen in which all the atoms are happy is possible. Okay, as if that weren't complicated enough, carbon has another trick up its sleeve. It can form a double bond with itself. Instead of sharing 1 pair of electrons, it shares 2 pairs of electrons, 4 electrons shared between 2 carbon atoms. If you're listening on audio tape, imagine 2 C's connected by an equal sign. And then you have to fill up the rest of carbon's needs with hydrogen. In this case, 2 hydrogens for each carbon. That leads to the compound C2H4, or ethene, which is the simplest member of the alkene series. Now, all the variations described above, chains, branches, rings, can also feature double bonds. The formulas differ from alkanes in that for each carbon-carbon double bond, there are 2 fewer hydrogens. A compound of special interest is the molecule benzene. That's C6H6, which is a ring of 6 carbons, and it has 3 double carbon-carbon bonds and 3 single carbon-carbon bonds shared around the ring. Benzene used to be commonly used as an industrial solvent and cleaning agent, but now it's really known to be carcinogenic, and so it isn't used nearly so much anymore. Nevertheless, it has a beautiful structure. And here we go again. Carbon can do something else. Carbon can form a triple bond with itself, in this case sharing 3 pairs of electrons, a total of 6 electrons shared between the 2 carbons. And in that case, each carbon only needs 1 additional hydrogen. You form, for example, the compound C2H2. That's acetylene. And if you've heard of acetylene torches, they burn with an extremely hot flame because there's so much energy in that carbon-carbon triple bond. The reason society values hydrocarbons so much is because of their unique and their valuable properties. All of these chemicals burn. They burn with intense heat and flame. They produce carbon dioxide and hydrogen oxide, that is water, as byproducts. So they're very clean burning fuels for that reason. The smallest of these molecules are typically gases or liquids, so propane and butane, for example, are fluids and therefore can be stored very easily as fuels. When you have larger straight chains, more massive molecules, then you start getting solids, and that's typical of candle wax, where the longer 20-carbon molecule typically forms a solid. But there's an interesting point here, because as you raise the temperature, those solids become liquids, and then the liquids become gas. And if you look at the way a candle behaves, you actually see a very interesting phenomenon taking place. In the lighted candle, you have the solid portion of the candle, which is at room temperature. Near the base of the flame, at temperatures of above about 100 degrees, you have a puddle of liquid. The liquid's pulled up into the wicks, and then at the hottest part of the flame, that molecule is turning into a gas, and it's the gas that's burning. So we see all 3 states of matter here. Turns out that branching and cyclic hydrocarbons usually have lower melting and lower boiling temperatures, because these are large, irregular molecules, and they don't pack together nearly as well as the straight chains that form the solid candle wax. Well, hydrocarbons are the easy part of carbon chemistry. And the chemistry of carbon becomes very, very quickly complicated as additional elements come into play. I want to look next at oxygen, element 8. It needs 2 extra electrons, so it often forms a double bond with carbon, sharing 4 electrons in total. You can think of a letter C next to the letter O with 2 lines drawn between them. And that double line, that equal sign, represents 2 pairs of electrons that are shared. So the oxygen's fully satisfied. It had 8 electrons to begin with. It sees 2 more, and now it has 10. And the carbon has 2 of its 4 electrons satisfied. So, for example, it can bound to 2 more hydrogens. And in that case, you get the compound formaldehyde, CH2O. The carbon has 3 neighbors. The oxygen shares 2 electrons. Each of the hydrogen shares 1. There are other larger aldehydes just formed by replacing the hydrogen with our CH3 group. Now, in carbon dioxide, CO2, you have a carbon with 2 neighboring oxygens. Each of those oxygens shares 2 pairs of electrons. Oxygen atoms can also form parts of rings. They can form parts of chains. In fact, anything that satisfies the 2 electrons that oxygen needs and the 4 that carbon needs is fair game. Let's look at another important group of atoms that involves oxygen, and that's the OH group. If you think about oxygen bound to 1 hydrogen, then hydrogen is fully satisfied. It now sees 2 electrons. The oxygen now has 9 electrons. It wants 1 more, so the OH group can form a single bond, can share a single pair of electrons with carbon. So if you start with methane, CH4, take away 1 hydrogen, which has a single bond, and replace it with an OH, which has a single bond. And you form methanol. That's the simplest of the alcohols. You can form larger and larger alcohols, once again, just by replacing another one of the hydrogens with CH3. For example, the 2-carbon alcohol is ethanol, C2H5OH. And that's the common alcohol of alcoholic beverages. It gets even more interesting. You can replace, with methane, you can replace 1 hydrogen with an OH group, 2 more hydrogens with an oxygen, and then you have the compound formic acid, CH4OH. H, O with 2 bonds, and OH. Formic acid is the simplest of what's called the carboxylic acids, which are absolutely vital in our own metabolic process. So far, we've only talked about 3 elements: carbon, hydrogen, and oxygen. So you might want to take a deep breath now, because I'm going to talk about nitrogen. That's element 7. It needs 3 extra electrons. And so here we have many different strategies. Nitrogen can form a triple bond with carbon. It can also form an NH group and form a double bond with carbon. Or you can have an NH2 group and form a single bond with carbon. Those are the amines, or the amino acids, which we'll find a lot about later on when we talk about biological molecules. Okay, going to the periodic table, we also have to look at some other elements. For example, in life, phosphorus, which lies immediately below nitrogen, and sulfur, which lies immediately below oxygen, are also very important elements. Indeed, sulfur acts very much like oxygen, with one important difference. Sulfur compounds are notoriously horrible smelling. They are the worst smelling chemicals you can imagine, and anybody who does sulfur organic chemistry had better have an isolated laboratory with a lot of ventilation. Phosphorus lies right below nitrogen, so phosphorus has a lot of similarities with nitrogen also in organic chemistry. And here again, the rules of the game are simple. Carbon wants 4 extra electrons. Hydrogen wants 1 extra electron. Oxygen and sulfur want 2 extra electrons. Nitrogen, phosphorus want 3 extra electrons. And so any compound you can imagine drawing that fills those criteria, that satisfies those needs, is fair game in organic chemistry. For the last part of this lecture, I want to shift my attention to 2 kinds of molecular bonding. All of these complex molecules we've described so far are compact. They're electrically neutral objects. That is, they're collections of atoms that don't need to give away any electrons, and they don't have an electric charge. So you might ask, why would something like CO2 or CH4 or H2O ever form a solid? Why would it ever form a liquid? Why wouldn't these just be gas molecules that go off and do their own thing? What kind of attraction could there be between neutral molecules? Well, it turns out that molecules are surrounded by electrons. So when 2 molecules approach each other, every electron, every proton in one molecule senses the presence of every electron and proton in the other molecule. And you start getting distortions of the electrons and protons, just slight shifts, but enough that you get slight areas of positive charge, slight areas of negative charge. And it turns out that these can actually cause an attraction between molecules. That's called the van der Waals interaction or van der Waals attraction, by which molecules can then bind together. This is a very common kind of bonding in minerals, and almost any kind of layer mineral, such as talc, which forms baby powder, talcum powder, also the graphite in your lead pencil. These are compounds in which van der Waals interactions hold layers of the material that are inherently electrically neutral together. Also, in many organic compounds, in candles, the waxy feel of the candle, or of soap, or of many other organic compounds is due to the van der Waals interactions that are holding these molecules loosely together. They're not ionically bonded or covalent bonded or metallic bonded. It's a separate kind of attraction. Now, the other kind of intermolecular force is called the hydrogen bond. But before I explain that bond to you, I have to tell you about a class of compounds that relies very heavily on hydrogen bonds. So far, all of the organic molecules I've discussed here have been relatively small, with just a few dozen atoms. But there's a very large class of organic molecules that has vast numbers, millions or billions or trillions of atoms. These are called polymers. Now, a polymer is in widespread use in everyday life in plastics, in many of the biological materials, your skin, the fibers of your tendons, your hair. These are long chain molecules that form from the interaction of what begin as very small molecules. But they latch on one to another, to another, to another, to make these incredibly long chains, chain-like molecules that then form most of the fibers in the natural world. Well, plastics form then from complexly intertwined strands of polymers. The plastics you use in your everyday life then are really interesting structures because it's like a set of fibers, bundles of fibers interwoven. And yet those fibers would normally just slide past each other unless there was some other kind of bonding. And that's where hydrogen bonding comes in. If you think about the surface of a molecule, you're going to have a certain number of hydrogen atoms just exposed on the surface. In other places, you may have oxygen atoms exposed at the surface. And these particular atoms tend to develop local charges. Hydrogens very often tend to be slightly positive on their surfaces, while oxygens very often tend to be very negative on the surface of an otherwise neutral molecule. And so if you can juxtapose two strands or two molecules so that the positive and negative charges become opposite each other, you can then start forming very strong bonds between them. And this is exactly what happens in hydrogen bonding. This is what makes plastics strong, even though they're made of neutral molecules that are interacting. It's also an extremely important bond in everyday water. If we look at the H2O molecules of water and think about ice, you'll see what I mean. H2O is a neutral molecule. 2 hydrogens, 1 oxygen in a neutral unit. And yet ice is an extremely strong substance. The reason is because every water molecule in ice is hydrogen bonded to others. The hydrogens see other oxygens, the oxygens see other hydrogens. That forms an intense cross-linking of these hydrogen bonds. And I can demonstrate that with a piece of ice. What you're going to see in this demonstration is that ice actually behaves very much like an ionic compound. If you take a piece of ice, it's transparent, just like ionic compounds. If you hit it with a hammer, it shatters, just like ionic compounds. It's brittle, and indeed the pieces could be stuck right back together, if you will. A simple demonstration shows the similarity between the hydrogen-bonded ice and ionic bonding. Ice is transparent, and it's hard. And if you break it with a hammer, it splits very much like a ceramic. The resulting pieces then are sharp, they have edges, and they fit right back together, just like a ceramic cup when it's broken. Well, to summarize this lecture, we've seen that the chemistry of carbon is extraordinarily rich and it's diverse because of 2 factors. First, every carbon atom needs 4 additional electrons. And the second reason is that it can satisfy the need for these 4 electrons by bonding not only to oxygen or to hydrogen, nitrogen, phosphorus, but also to itself, forming carbon backbones and rings and branches of incredible complexity. Literally millions of carbon-based chemicals play this bonding game. These molecules then link together using van der Waals attractions and hydrogen bonding to provide most of the physical materials in our surroundings and in ourselves. In the next lecture, we'll continue our exploration of the material world by examining the states of matter, solids, liquids, gases, and plasmas.